Today's webinar is on Static and Dynamic Headspace 411, Theory and Method Development, presented by Roger Bardsley.
I'd like to talk about the two Autosampler Headspace systems that we have that we're going to talk about today. The HT3 is a 60-position autosampler. We have a 10-position sample platen, which allows for overlapping, which we'll discuss a little bit later. The sample can be heated up to 300 degrees. It has the optional dynamic trap capability, so you also can run the loop and trap methods in the same sequence. It has a MOM method development software for the sequence. We use a mass flow controller with this, and it comes with a standard 1 mil loop, and other sizes are available. The Versa automated headspace vial sampler has a smaller footprint. It's only 1 foot wide. It is a static only. It has a 20-position autosampler, a single vial platen. The sample can be heated up to 200 degrees C, and it also has the MOM method development software for the sequence. It is pressure regulated. It comes with a standard 1 mil loop, and other sizes are available. Moving on to our webinar today that we're going to talk about static and dynamic headspace 411, we're going to cover a little bit about static and dynamic theory. Then we're going to talk about headspace method selection, and we'll talk a little bit about the method optimization mode part for the sequence, and then I'm going to go into a little bit of the tips and tricks that we use to get these methods working. First of all, headspace theory is the placement of a sample in a vial, heating that up, creating an equilibrium between the matrix and the gas phase. The difference between static and dynamic headspace is that in dynamic headspace, you sweep the headspace vial and take that sample out and put it onto a trap. So as you can see over time, you'll exhaust the headspace of components. In static headspace, you create that equilibrium, then you take a portion of that, put it into a loop, and then analyze that with the GC mass spec. Excuse me. Moving on to talking about the static headspace, which we call the loop methods. We have the two Versa and HT3 that offer this for you. And I'm going to go a little bit into the theory. Excuse me. Partition, we're going to talk a little bit about partition coefficients first, then I'll go over the universal gas law, and then I'm going to talk about phase ratios, which has some interesting information with. Partition coefficients is equal to the concentration in the matrix, the CM, over the concentration in the headspace or the gas phase. You can also use that as the concentration in the matrix is equal to the partition coefficient times the concentration in the gas phase. Fairly simple equation. Typical values of some compounds in water: hexane, benzene, toluene, xylenes, things that don't like to be dissolved in water, have very low partition coefficients, or things that are more liking water, like your methanols, ethanol, propanols, and the acetaldehydes, have a little bit higher partition coefficient. One way to change the partition coefficient is to add modifiers, which can be salts, potassium chloride, ammonium salts, things like that, acids or base, depending on your compound, going down to pH 2, going up to about pH 10 can help. Excuse me. And also the sample matrix itself can create a modifier to it. When we were doing paint samples, we realized that we could take paint samples which are water-based, latex paint, up over 100 degrees and get some better results from that. Talking about the universal gas law, PV equals nRT. The constants here that we have in headspace are the volume of the headspace vial. The number of moles are how much you put in there, and then there's also the universal gas constant, and those are all constant. We can change this by adjusting the pressure in the vial and or the temperature in the vial, and this is what we do with headspace. Now moving on to phase ratio, talking about the mass balance equation, the mass of the original sample, when you put it into a headspace vial, will be kind of divided between the mass in the gas phase and the mass in the matrix phase, whether that be a polymer, soil sample, or a liquid sample. we know that the mass in the original sample, because it has no headspace over it, is the concentration of the original times the volume of the matrix, whether it be 10 mils of liquid, 2 grams of a solid, or whatever. In the gas phase, that mass will be equal to the concentration of the gas times the volume of the gas. And in the matrix, it'll be what's in the matrix, in the concentration of the matrix, times the volume of the matrix. Putting in the partition coefficient in there, we remember that Cm is equal to the partition coefficient times concentration in the gas phase. Combining these equations, we can see that the original concentration will be equal to the concentration in the gas times the partition coefficient plus the phase ratio. We define the phase ratio as the volume in the gas over the volume of the mass. This is an interesting concept, and by changing that phase ratio, we can actually increase our detection limits. Teledyne Tekmar offers 3 vial options. We have the 9 mil vial, the 12 mil vial, and the 22 mil vial. For the HT3, we need to use inserts so we maintain the same height as our 22 mil vials. I have included part numbers here if you are interested. Moving on to the phase ratio. In a 9 mil vial, the maximum volume that we can put in there is 5 mils. For a 12 mil vial, we can put 8 mils. 22 mil vials, we can put 17 mils. So what we did on this experiment was we took a standard concentration of some environmental samples in the water. We added that to the vials in 1, 2, 5, 10, and 15 mil increments. Then we calculated out the phase ratio by just taking what was the gas divided by the volume in the gas. Looking at benzene, we can see that you do get a drastic increase in the detection limit with these phase ratios. I've included the theory because we had this higher concentration in each vial, but as you can see, there's a drastic difference here. Now, thinking about this, if you are unlimited on samples, we suggest 22 mil vial. However, if you have smaller sample sizes, say a 2 mil, you can use the same phase ratio as a 5 mils in a 22 mil vial and get reasonable results. It works fairly well for compounds that have a good partition coefficient like benzene. Looking at methyl tert-butyl ether, we can see that the theory here, as we increase the concentration, we don't see that same phase ratio as we saw in benzene, but we still see a good phase ratio by increasing the sample size. Why is this, you ask? What do? We could go into the vapor pressures and Dalton's laws, talk about Rail's law here, but what I'd like to point out is you need to know your sample, what it is, and it also helps to keep your sample and standards similar. Create your sample, your standard, if you can, in the same matrix as your sample. With water or liquid, that's fairly easy. Now I'd like to show, when we're talking about static, how does our system operate? We have a little graphics here. I apologize if you cannot see the graphics on your screen. It will be available on our YouTube channel after we download this. So we come in from the gas tank through our mass flow controller on the HT3 with the Versa. This will be a pressure regulator. We go through the pressure valve, and as you can see, if you have a loop-only mode, you won't see the sweep valve or the bypass or trap valves. So in a loop-only mode, it will continue to go through the loop, and we're going to come down to the vial and do what we call the pressurized step. At this point, we're going to go into our 2-stage needle on the HT3, 1-stage needle on the Versa, and pressurize that vial to a constant pressure, remembering PD equals nRT. Once we pressurize that vial to the pressure, what we're going to do is release that pressure back through to go back onto the loop and out the vent. And we'll see that here as it comes out. We'll fill that loop. We're now going to go to what's called the loop fill pressure. And at that point, we're going to shut the system off, and we're going to prepare to inject it onto the GC. As you can see here, we have a transfer line coming in, and we'll load that up by throwing this 8-port valve here and inject the sample onto the GC. So here comes the GC gas coming now, sweeping that loop volume onto the GC. That is what we call the static headspace, or a loop fill. Now I'd like to cover what we do when we do dynamic headspace or trap. The HT3 is the only headspace autosampler that we have that offers this functionality. It's an offshoot of Teledyne Tekmar purge and trap technology, except for that the gas above the sample is swept. We do not purge through the sample. It was developed to use straight tube traps following EPA 524.2 requirements. This says that you should use a 25 centimeter length tube that's about 0.105 inch ID. It comes with standard packings. Those packings are 10X, silica gel, charcoal, OV1, Carbopac B, Carbopac C, or Carbosiv 3, Carboxin 1000, or Carboxin 1001. And these are all standard traps that are available with different amounts of these compounds in them. It also can do custom packing because this is an open tube. For those that remember pack columns and had to pack the old glass columns way back when, the same technique is used to pack these straight tube traps, where you take and close off one end, pull your packing material, whatever that trap material you'd like to use, and then sealing that up and use that on the system. It's a little different from static headspace. Partition coefficients, the phase ratios, and the universal gas laws kind of still come into effect, but because we're sweeping that headspace, we're constantly changing that equilibrium. So the sample headspace is swept versus removing a volume of that sample headspace as you would in a static headspace system. To show you the difference on the trap, again, we have an animation, and we're going to come in through the mass flow controller so we can control that flow, whether it be helium or nitrogen. So you can purge the sample with 400 mils of gas, 500 mils of gas, etc. So we're going to sweep that vial, and as you can see in this animation, we're going to come down through the second stage of that needle and sweep that vial. And then that's going to go back up through the first stage of the needle out onto the trap. And as we can see here now, we're sweeping that sample, and it's going to come across the trap to be trapped with the untrapped material going out through the vent. Once we get our trap time completed, we will preheat that trap, and then the GC, through the turning of that 8-port valve, will take that trap sample and transfer that onto the GC transfer line. Now I want to go start working on the headspace method selection. It's very similar to what you've learned throughout the careers of the 5 W's and H. Who, what, where, when, why, and how. Who and where would this headspace method be used? We know that we have customers in the food industry, flavors industries, pharmaceuticals, forensics. Blood alcohol is a very large user of this. Environmental samples, 524 type samples, water samples, soil samples, sludge samples can be used with headspace. Polymer samples are being used. The automobile industry uses it. Diesel, for biodiesel, looking at the methanol concentration in there. Excuse me. Coatings and paints. Again, we talked about the paint samples that we used earlier. Personal care, hand sanitizer. We've tested that type of samples. Oil and gas industry. We've did the fracking methane issue out of water, pest control, and there's a lot of others out there that we know of that customers are using Headspace systems with. The what of Headspace. It's a sample preparation technique for GC and GCMS. If your sample is performed with a LC, it won't work with Headspace probably. The vial is typically heated, as we talked earlier. The volatiles separate from the sample matrix. That's where we're creating the equilibrium, either through static or dynamic, where we purge at it. Static is very useful for percent to parts per trillion sample concentrations. Some of you may think, how can you get parts per trillion with static? We have a couple application notes out there for VPH, volatile petroleum hydrocarbons, in water, where we were able to get down to parts per trillion concentrations by using SIM mass spec, looking at the specific ions for those compounds only. Dynamic is typically used when you get down to the parts per million and definitely the parts per trillion concentration. When would you want to use Headspace? You have a method where you're using a solvent extraction. By going to Headspace, you can reduce the solvent you may have to use, or no solvents at all. That's a very labor-intensive process also when you're sitting there shaking a sample and extracting it. Looking at greener chemistry, again, the solvent issue. If you can use a method that doesn't use a solvent that is considered hazardous, then you don't have the solvent going up a fume hood. For example, methylene chloride soxyl extractions. The waste disposal cost goes down because now you no longer have that solvent going to a waste facility. The why. There may be a regulation. The ones that I can think of are USP 467 for residual solvents in pharmaceuticals. I know International also has a similar Headspace method for residual solvents in pharmaceuticals. You may be looking at 5035 by EPA, where you're taking a soil sample that's very highly concentrated in gasoline, and you want to pre-screen that before you put it onto a purge and trap system to make sure you don't contaminate your purge and trap. The other thing that the why would be to reduce the syringe inlet and column maintenance. In the beverage industry, would you want to take a soda and inject it onto your GC? That cruds up the inlet very quickly and can put compounds on the column that you don't want to. It may make your syringe sticky. If you have an autosampler, it may cause your plunger to jam up in the autosampler. So Headspace can reduce that. You can modify the matrix to fit the analysis. For example, with the paint, we just put the paint sample into the Headspace file and ran it. There was no additional water that was needed or anything. The matrix there modified it to where we could see the compounds of interest. You can directly analyze solid samples in the polymer industry, where you take a piece of polymer and put it into the vial and just run that without maybe dissolving it with THF or DMF, tetrahydrofuran or dimethyl formamide. High concentration samples can be tested. We've tested hand sanitizer, which has a high concentration of ethanol. There again, the hand sanitizer, if you'd inject that onto a GC inlet, the material, the extra material in the hand sanitizer would crud up your inlet very quick, so you'd have to recalibrate with a new inlet. It also can give you increased sensitivity for samples. What compounds would you want to look at? First of all, they have to be testable by a gas chromatograph. You need to have the separation and detection there. For example, if you're looking for 1 femtogram, if you cannot see it on the GC system you have, the Headspace Autosampler is not going to give you that increased sensitivity. The sample needs to be volatile. The Versa can go up to 200 degrees C. The HT3 does go up to 300 degrees C, which is very useful for the polymer industry. It helps to have current parameters, a GC method or a Headspace method or a process that you're currently doing that you'd like to change over to a Headspace method. The method for static, again, mentioned going from percent down to parts per thousand or parts per trillion. Sample volume is important. You can also do what's called a full evaporative technique, where you only put a small amount of a very volatile sample in there. For example, 100 microliters of water. Heat that up to 150 degrees and take that sample there. Lower sample amounts can be used. And again, I want to point out one caveat. We can get down to the parts per trillion on that if we use sim mass spec, the VPH application note that we have on our website. We also did benzene and sodas at very low levels by doing sim scan on a GC mass spec. If you're going to go to parts per billion to parts per trillion, again, static can be used. It's very compound specific, and it's mid to high parts per billion. Static, you can get down to parts per trillion with the simming, but typically we would do parts per billion to parts per trillion with the dynamic headspace method. What is the static headspace method? I have the two screens here up for you to look at, where we have the Versa on the left and the HT3 screen on the right. On the Versa, we have the GC cycle time, valve oven temperature, transfer line temperature, and the platen sample temperature. We also have the sample equilibration time. If you want a mixture sample, these next 4 steps are for the mixer. When we talk about pressurize, if you remember back to the animation, this is the pressure that we're going to pressurize the valve up to. So if you have 5 mils of water in there and you're heating it up to 40 degrees C, we're going to take that static valve pressure, which will be read off of the screen over here, and pressurize it up to 10 psi. We will then fill the loop by opening that valve and letting that pressure from the valve fill the loop down to 8 psi. With the HT3, we have similar steps. The first step you'll see here is the constant heat time. Because we allow overlapping with the HT3 by turning this on and filling out the GC cycle time, the GC cycle time being from the time the injection starts until the GC comes back ready for another injection, we can overlap a sample. For the forensics industry, where you're doing blood alcohols, the GC runtime for the blood alcohol may be 3 minutes based on your column and your GC parameters at an isocratic temperature. Yet the heat time for the sample may be 20 minutes. We will take that first sample, heat it for 20 minutes. At 3 minutes, the HT3 will drop another vial in there to prepare it to get ready for the next injection. At the end of the 20-minute equilibration time for the first sample, it'll inject the first sample. When that sample is done running, the second vial has already been heated for 20 minutes. It will be injected shortly thereafter for another 3-minute run. So as you can see with the HT3, with the overlapping mode, we can perform more samples in a shorter amount of time than we could on a Versa. With a Versa, this would be, you'd wait for 20 minutes, make a 3-minute injection, the sample would have to heat for another 20 minutes for another 3-minute injection. So as you can see, the HT3 gives you a lot faster turnaround time for samples. The dynamic method has the same valve oven temperature, transfer line temperature, and sample temperature as we saw on the static methods. We do have trap standby temperatures, dry purge time, the desorb times, and the trap bake, because again, we put the trap in there, so we want to do a similar trapping as we would do with maybe a purge and trap method. The other thing I'd like to point out on our screens is that with all of our screens, there is an instrument status over here to the right-hand side that will inform you of what the current status of the instrument is. The mode is ready. It tells you you need to press step to continue, so you come up here and press step. You see some of the same functionalities over here. What is the schedule running? What is the current line of that schedule? What is the active method? What is the pressure of the current system? What's the transfer line temperature and the oven platen temperature? Again, with the trap, because we have more parameters, it'll tell you what the transfer line temperature is, the oven temperature. What is the trap temperature? So you can see the trap is heating up or not. And that'll become important when we talk a little bit about the maintenance on, or the system tips and tricks. I want to go over the method optimization mode. This is an opportunity when you're developing a method to create a more rugged method. With the static loop methods, both the Versa and the HT3 software have the opportunity to do that. What you do is you open a schedule, and up here at the top of both of them, you'll see what's called the MOM Builder. When you click on the MOM Builder, it'll open up a second window. With the Versa, it has a graphical interface to it. With the HT3, there is no graphics because this is an older software version. It gives you, for static, the ability to modify the platen temperature, the sample equilibration time, mixing level, pressurized, loop fill pressure, and the inject time. With the Versa, some of the similar features are available. Looking at the screen with the Versa, selecting the platen sample temperature is something I may want to change. So I'm going to set my start value at 40. I would set my offset value at whatever offset I want. Typically, I'll step it up 10 degrees per minute. How many samples do I want to run will be all filled out here. Similarly, with the HT3 MOM, pick the loop method, pick that method, pick the platen sample temperature, select the start time, place in a step value. You cannot see it on this screen, but the stop is grayed out. As you place a step value number in here, this will change, and as you increase that number, this will change, telling you how high you're going. How many samples do you want to do per temperature, and then what is the start position? When you click on Apply, this is what you'll see for the Versa. On the HT3, I've went ahead and placed in those values, and we'll look at what happens when you click Apply. As you can see over here, it creates the entire schedule or sequence for you automatically. Over here, platen sample temperature of 40 degrees for 3 samples, then it steps up to 50 degrees for 3 samples, then it steps up to 60 degrees for 3 samples, 70 and 80. The HT3 does a similar thing, 25 degrees, then 35 degrees for 3 samples, 45, 55, 65. Your next step is to put in 15 of your samples that you've selected and press Run. Selecting Start here to begin. Now I'd like to talk about the method optimization mode for the dynamic methods. This is only available on the HT3. We can vary the trap sweep temperature, sample temperature, the sample preheat time. Say, for example, you have a polymer and you want to see if I preheat that sample for 5 minutes and do 10-minute increments, does that help me heat that sample up better so when I sweep it and trap that sample that I get better sensitivity? Sweep flow rate, sweep flow times, dry purge if you have a wet sample. Does a longer dry purge time or dry purge flow help? Or even a dry purge temperature for the trap. This is an interesting thing in that when we did some work for 1,4-dioxane, we found out that if we heated up the trap just a little bit during that dry purge time to take off the water, we could get better sensitivity for the dioxanes. So there again, you select your method, select trap, select the method variable that you want to change, start time of 25, step value of 10. I want to go up 5 steps, and as you can see, it set that to 65. I'm going to do 3 samples. It tells me my stop position will be 15. When I select Apply, again, it creates the method. I get my samples ready, put them into the Autosampler, and press Start. Now I want to go over method development tips. There's 4 methods I kind of want to cover that a scientist could come up with. First, I want to call the mystery headspace method. The next one is the convert headspace method. Then there's a modify headspace method we're going to talk about. And finally, a current headspace method. For a mystery headspace method, you have a polymer of 1 compound of interest that we were going to look for. First, we would develop a GC method The detector would be either mass spec or FID or anything else. What's the sensitivity we want to go to? Percent or parts per million. That would kind of dictate which detector we may want to use. The column, in this instance, it was a light volatile organic compound, so we just used a typical EPA type column that would separate out some of the lighter volatiles. We created an oven profile that was sufficient to provide reasonable retention time for this compound. So here's our method. We set up using MOM, we set up a series of temperatures starting from 60 degrees, going up 10 degree steps. And as you can see, the compound of interest here did start increasing. As we got to the higher temperatures, we also noticed that we were starting to overload the column. And this is one thing you'd want to take into consideration when you're developing the method. The Headspace autosamplers, both of them will send the sample over to the GC. If you overload the GC with that sample, it'll behave just like the GC will and overload your column. You may want to change split ratios. You may want to change column size to get that higher capability of putting more sample onto that column. So as you can see here, from our study, we created a graph of using the peak area and observed that when we got to those higher temperatures, we were probably overloading the column. That system had maxed out the amount of sample that it could separate efficiently. The next step in this mystery headspace method was, what about sample heating time? So we took a standard heating time that we found in the process and ran it with MOM by changing the sample equilibration time in steps. And as you can see here, we found that at about 30 to 40 minutes, we had already reached that equilibrium. So we put that into a method. The final step in this mystery headspace method would be to check the linearity. As I change that sample volume, the amount of sample going onto the GC column, do I have a linear method? Because this was a polymer from the ASTM has informed us that there's a bias if the sample mass to the volume in the vial exceeds 10. So we stayed well below the 220 milligrams for the polymer and created a linear curve. And as you can see here, we got a very decent linear curve. Moving on, convert a headspace method. You have a GC method that you want to convert to a headspace method. This one we used fusel alcohols. It is a direct inject when we change it over to the headspace. The method we followed was the government's TM200 method. It's an external standard calculation, and all required is a correlation coefficient greater than 0.99 for 3 standards. We modified the method to work with the static HT3 and Versa headspace. So we set up the temperatures, made sure the chromatography was good, looked at different temperatures, 40, 50, 60, 70, 80 degrees, used a concentration range, and then we looked at the correlation coefficient for that concentration range and the relative standard deviation to pick a good temperature for this method. As you can see with the correlation coefficient, 60, 70, and 80 degrees was reasonable. However, with the percent RSDs for that calibration curve, we got our best RSD at 60 degrees. So we created a method. We used 10 mils of the standards. We did a 5-point calibration curve. And this is the results we got. Very good data. As a result, static headspace method met the requirements of the TM200 method. Simple sample prep, you just put the sample in there, and multiple samples can be tested without inlet and column maintenance. Moving on, when you modify a headspace method, we looked at hexanal and rice by dynamic headspace, performing a trap one. We had a reference in an article for this, so we did similar things of what they did in the article. We used 1 gram of lightly ground rice. We also spiked it with a hexanal standard to create a calibration curve. Part of that was because The rice creates a matrix effect, so you had to calculate for that. As in the literature, we used 30 degrees C, and we used a 10x trap. This is the linear calibration curve. The standard by itself, you can see here, has a very good calibration curve. However, the rice does create a matrix effect, so we had to create the calibration curve with that. Also, you notice the difference here at the 0 point. The rice does have some hexanal in it that we used. We could not find a hexanal-free rice, so we did kind of a standard edition spiking. We created 7 samples and calculated that, and as you can see with the dynamic, we got an RSD of 9% with an average recovery of sample of nanograms per gram of hexanal in rice of 90 nanograms per gram. Hexanal was adequately detected in the rice. It confirms in the literature that a standard curve must be prepared in a rice matrix. It's a simple method for testing rice for randomicity. And again, multiple samples can be tested without the inlet and column maintenance. Moving on, you have a current Headspace method that you may want to use. In this instance, we did 467, USP 467, residual solvents in pharmaceuticals. There's 2 columns for that. We plugged their numbers, 80 degrees C, 45-minute sample equilibrium time, into the method. Made sure the chromatography was there for these. These are class 1 compounds for those of you in the pharmaceutical industry. Created a calibration range so we could get an R-squared value. We also did 3 samples at the concentration required by the pharmaceutical method. And we also looked at signal-to-noise ratio for the class 1s, which is a requirement of the pharmaceutical method. And as you can see for the class 1 compounds, we met all the requirements, got very good RSDs for these compounds. This one, as I showed in the previous page, co-elutes with that peak, so you cannot see it. For the class 2A compounds, again, the 2 columns that we used, following the USP method. For the first set of those, again, the values are here with the ranges. The RSD of 3 samples prepared at the concentration in the pharmaceutical method, and then the correlation coefficient for the curve that we created. And here's the second set of those compounds. Class 2B, again, made sure the chromatography looked good for the 2 columns, the G43 and the G16. And here's the results for those also. Now that we've covered methods to work with, I want to cover a little bit of troubleshooting and maintenance tips. The first here is, first thing you want to do is consult the PDFs in the manual directories, or also then you want to watch during analysis. There's history data we wanted to look at, perform a leak check, do diagnostics. Sometimes with the HT3, the 8-port valve can get untrained, so we have to retrain that. And sometimes there may be contamination in the system. So I want to cover all of these for doing maintenance on the systems. First of all, for the Versa, as within all of our documents, underneath the Versa directory that was loaded during install, there are 3 PDF files. As you can see with this first one here, a very intricate diagram of the electronics. When you blow this up, you'll actually see that a lot of these numbers are the part numbers for that part, for the board, for the connector. The other file is for the flow diagram. With the HT3, the similar thing, under the manuals directory, we include quite a few manuals with that. We have assembly drawings. We have the user manual available. We also have the wiring diagram. Again, these things will also have part numbers in them for you. We have the flow diagrams that shows you during the different steps of the instrument, what is the flow doing. Plumbing diagrams, and even the plumbing module assemblies, which again has the part numbers with them. Watching during analysis. Now I know some people may say, well, Mr. Roger told me that during the HT3 or Versa run I have to watch it during the analysis. What I'm suggesting here is to kind of keep an eye on it. In the years in my laboratory experience, I can walk in the lab and sometimes hear something that's not quite right. As you walk past the instrument through the day, do things look right? Does it sound right? Are the sounds similar? If you become accustomed to that, sometimes you can hear when something doesn't go right. Also, watching during analysis, what I'm suggesting is, while it's doing a pressurizing of the valve, is the pressurized performing properly? And we have those here that are automatically reads during the sample analysis. Same thing with the HT3 during the trap. Are the pressures performing correctly? Is the trap heating up when it's supposed to? Those are all things that we show on the screen. So as you're watching, you'll be able to say, well, the trap didn't heat up hot enough. You come in, you find that your data doesn't look right and something went wrong possibly. The first thing we would do is go into Versa, click on View, and select History. Here I've displayed all the history that you're available to look at during this, through this history. You can also sort the history to look at just method uploads, mode change attempts, or whatever. That is all available through the software. With the HT3, you click on the radio button for history. You can also go to View and select History there. It'll pull up the history for times that you want to take a look at. As you can see here in this history, the static valve pressure is a pressure that the valve was heated up to in the platen. When it reached equilibrium, we pressurized it up to 15, and then when we filled the loop, it filled it down to 11. This is a useful tool for troubleshooting what may have happened. Maybe the valve didn't get sealed properly. So I'd go back to the Autosampler and is the valve cap loose? Again, this is a good way to do some troubleshooting for the HT3. Leak check. Something didn't work. Both of our Autosamplers allow you to leak check them. By clicking on the radio button for the HT3 here, or the leak check here on the Versa, will open up other panels for you that have step-by-step instructions of what you need to do. With the HT3, it'll open up another window. With the 8 Versa, it'll open up another window. With the HT3, it'll give you messages here over what steps you need to take. The first one is you need to put a sealed valve into step number 1. Once you get that done, you click on step. Diagnostics. Leak check passed or may have failed. There's some diagnostics you can do. This one here, unless you're very skilled, I would not do much with, because it moves the motors, and as it says down here in the caution, you can create mechanical damage to your system. I would only use the screen if you were talking to tech support and they ask you to make a movement on this one. The other thing that you can do here is look at your valves. You can have this open during a run to see, is the valve opening when it should. Similarly here on the Versa, you see the valves. Where is the 6-port valve? With the HT3, we have the valve co-valve that rotates the 8-port valve. What position is it in? You can set system pressure if you want to on the HT3. And this is all available under the tools, diagnostics. In the advanced with the HT3, by looking at this, you can see, are these sensors clicking at the right time? If you have a run was going and the power went out during the run, you can come in here and look at it and see, are there valves still in the HT3's platen? You can unload that platen automatically and it'll automatically take those valves back out so you can start your run over again. With the Versa, the Autosampler tab allows you to move the Autosampler. Again, I would use extreme caution on this and make sure you're talking to our technical support people. As you can see down here, it says the elevator or sensor is blocked. So if I would attempt to move the elevator, it would not move. And again, definitely talk to technical support when you're in these screens, please. The other part of diagnostics that is useful is called the benchmark. Is everything working in the system? I'm going to start with the Versa benchmark first. It has fewer parts and is only static only with one platen. So by clicking on the benchmark, putting in the name there, it'll go through automatic tests. Some of them will ask you for, like on the LED test, is the LED light on? Is the LED light blinking? Is the LED light off? Is the beeper working? It'll then go through the mechanical test automatically. When it gets down here to some of these things, it'll ask you, is a carousel in position 1? When it's done, all these should have green checks on them. If it doesn't, that's where tech support would come in handy. With the HT3, the benchmark is under the diagnostics tools. Click on the benchmark tab, put your name in here. And again, it'll go through some automatic tests. As you can see here on this test, it's a user entry test. Is the pressurized valve LED on? You have to take off the back cover and that physically say that yes, the LED light is on. Again, it goes through numerous tests. Some of these are automatic, some of these are user interfaced. Talking about retraining the 8-port valve. This is a step that you should only do if tech support asks you to do that. We have a short video here. If you cannot see the video, it will be available when we post this to our YouTube. First of all, you take off the right side cover of the HT3. You will disconnect the cable to the 8-port valve, as you can see here. You will then go to the software, and you will switch the Valco valve back and forth between the A and B position. And we'll see that here in a second. You'll see the lights change. When you've done that a couple times, then you will plug the connector back in, and you will re-switch the Valco valve again, and you will hear a sound difference. It'll be kind of a low-grade grunt, and then it'll turn to a very crisp yeet, and that's when you know that you've retrained the valve properly. Again, this is something for your information. Talking to tech support at the time would be helpful. And with that is the conclusion of my webinar today. Oh, I'm sorry. I have one more slide. Contamination in the system. How I take care of that is typically first I'll heat the system up. I'll heat the valve and the up to a high temperature. If I need to flush something out, for example, the needle gets clogged, which happens very infrequently, I'll take a solvent that doesn't interfere with, and again, talking to tech support can help that. I thank you for attending today's webinar, and we'll be talking to you later.